Somewhere in the Arabian Sea, at 2 in the morning, a $2.50 billion destroyer turns its bow away from the Iranian coastline and starts heading south. Not because it has been hit, not because the crew is exhausted, but because 12 hours earlier, that ship fired its final Tomahawk cruise missile, cell number 96, into an IRGC command node buried deep inside the Zagros Mountains. The missile did its job. The target is rubble, the ship is undamaged, the crew is ready, but the ship is leaving. 96 vertical launch cells, every single one of them empty. Each missile weighs 3,500 pounds. Each one is 20 feet 6 inches long. Each one costs around $2 million, and this ship has no way to put even one new missile back into those cells. Not out here, not in open ocean. The only place this destroyer can reload is alongside a concrete pier with a shore-based crane, and the nearest one is more than 2,000 nautical miles south, at Diego Garcia. 1 week to get there, 3 to 5 days under the crane. 1 week to get back, 3 weeks out of the fight. So here is the absurdity. A warship built to dominate the electromagnetic spectrum, carrying the most advanced combat system ever put to sea, is sidelined by an empty magazine and the absence of a machine capable of filling it. And the machine does exist. It has been tested, it works, but it is still stuck in development. Proven twice at sea, still not fielded across the fleet. It arrived one war too late. In less than 5 weeks, 850 Tomahawks have left American launch tubes, more than in the entire Iraq War. The highest number of cruise missiles fired in a single campaign in history. And the question no headline is asking is not how many we fired, it is how we reload. If that question matters to you, subscribe to Navy Decoded. We do not celebrate weapons here, we calculate whether they last. To understand why a navy that spends more on its fleet than the next 9 nations combined still cannot reload its own missiles at sea, we have to begin with the physics that made it impossible. Start with the cell. The Mark 41 vertical launching system is the backbone of American surface warfare. More than 60 warships carry it. Every Arleigh Burke destroyer, every Ticonderoga cruiser. Each cell is a steel tube roughly 25 inches square, just wide enough to accept a missile canister with only inches of clearance on either side. Now think about what goes inside it. A Tomahawk Block 5 cruise missile in its launch canister is 20 feet 6 inches long and weighs 3,500 pounds. Inside that canister is a turbojet engine, a warhead packed with several hundred pounds of explosive, and a solid rocket booster filled with propellant. This is not forgiving cargo. This is a steel tube loaded with explosive force, designed to be lowered into another steel sleeve with surgical precision. On a concrete pier, with a shore-based crane locked to the ground, that operation is routine. The crane lifts the canister descends vertically. Guide rails align it. It slides in. Done. The earth does not move. The pier does not roll. Gravity pulls straight down. Now try that same operation at sea. A ship in open ocean moves in 6 axes at once. Pitch, where the bow rises and falls. Roll, where the hull tilts side to side. Heave, where the entire ship lifts and drops with the swell. Yaw, sway, surge. Every second, the deck under your feet shifts in a direction the crane did not predict. And here is the physics that killed the entire idea. The moment you suspend a 500-pound canister from a crane cable, that canister becomes a pendulum. The ship rolls left, the cable swings right, the ship heaves upward, the canister drops. The delay between the ship's movement and the canister's inertia creates an oscillation you cannot fully control. Even at sea state 3, moderate swells, nothing dramatic, the amplitude of that pendulum swing exceeds the clearance tolerance of the VLS cell. The canister slams into the cell wall at an angle. Steel meets steel, and inside that canister are rocket propellant and a warhead. One bad impact, and the crew is not reloading. The crew is evacuating. That is why the Navy stopped trying, because the math does not negotiate. The early Arleigh Burke destroyers, Flight 1 and Flight 2, DDG-51 through DDG-78, carried a partial solution. 2 strike-down modules, one forward and one aft, each containing a small crane designed to lower canisters into VLS cells. But each module took up the space of 3 missile cells, cutting the ship's total capacity from 96 down to 90. And then a second problem appeared, one the pendulum equation did not even fully explain. Those cranes were rated for shorter, lighter canisters, not the full-weight Tomahawk. So even on calm days they could not reliably handle the very missile that would come to define 21st century naval strike warfare. In theory, those cranes allowed at-sea reloading of smaller munitions. In practice, they were rated for calm seas only, and calm seas in the Arabian Sea or the Western Pacific are conditions that exist on calendars, not on oceans. After years of testing, the Navy reached a conclusion. The pendulum physics made at-sea VLS reloading operationally impractical, so it made a trade. Starting with Flight TOI-AA, DDG-79 onward, the Navy removed both strike-down cranes entirely. In their place, it installed 6 additional VLS cells. Total capacity went from 90 back to 96, 6 more missiles. And in exchange, the United States Navy permanently gave up the ability to reload its primary weapon system at sea. That trade made sense in 1999. The assumption behind it was straightforward. Wars would be short, precision strike campaigns would be surgical, and 96 missiles would be more than enough to finish the fight before the ship ever had to return to port. For 25 years, that bet held. Then came Epic Fury. Now let us be precise about what those 96 cells actually delivered. In the first 5 weeks of Operation Epic Fury, American destroyers and submarines launched 850 cruise missiles. No other navy on Earth has the industrial capacity, the training, or the logistics chain required to deliver that amount of precision firepower across that distance. So this is not a story about a weapon that failed. This is a story about a weapon that worked so completely, so relentlessly, that it outran the system built to sustain it. CENTCOM confirmed more than 12,000 strike sorties against targets across the full depth of Iranian territory. Tomahawks hit IRGC command and control nodes. They destroyed ballistic missile storage facilities, the backbone of Iran's threat architecture. They hit drone production lines. They cratered military airfields. They dismantled naval bases. More than 155 Iranian warships were destroyed or rendered inoperable, many of them caught in port, unable to sortie before the missiles arrived. The opening salvo on February 28 dismantled Iran's senior military leadership. Follow-on strikes pushed the nuclear program back by years. The President of the United States declared the core strategic objectives near completion within 5 weeks. 850 Tomahawks, roughly $1.70 billion in precision ordnance, and every one of them worked. But volume creates a problem that firepower alone cannot solve. Every missile that leaves a VLS cell is one more cell that goes dark, and the only way to turn that cell back on, the only way to reload it, is at a concrete pier with a shore crane 2,000 nautical miles from the fight. Now run the arithmetic. An Arleigh Burke Flight 3 destroyer carries 96 VLS cells. At full combat tempo, firing Tomahawks at time-sensitive targets while also using SM-6 interceptors to defend the carrier strike group, those cells do not empty in weeks. They empty in days. And when the final cell fires, the ship has 2 choices: stay on station with no offensive capability and reduced air defense depth, or leave. It leaves. And that is where the bleeding starts. The destroyer heads toward the nearest port with VLS loading infrastructure. Bahrain has the equipment. But during Epic Fury, Bahrain's port facilities are saturated. Every pier is occupied. Cranes are working around the clock. Ships are queued in the harbor, waiting their turn. If Bahrain is full, the next option is Diego Garcia, 2,500 nautical miles south. After that comes Suda Bay in Crete, 3,400 nautical miles northwest, 1 week out, 3 to 5 days under the crane, 1 week back. That is a minimum of 3 weeks in which a $2.50 billion warship contributes nothing to the fight. Now multiply that problem. If the fleet has 10 destroyers on station, and combat tempo burns through their magazines in 5 to 7 days, then at any given moment, roughly a third of the force is in transit to reload. Another third is waiting at the pier, and the remaining third is the only part actually fighting. So the Navy does not have a firepower problem. It has a presence problem created by the success of its own firepower. And this is not new. In the Red Sea in 2024, destroyers defending commercial shipping from Houthi drones and missiles burned through their SM-2 and SM-6 interceptors within weeks. With no ability to reload at sea, those ships had to withdraw to Mediterranean ports, Suda Bay, Sigonella, Rota, and every time one ship left, it created gaps in the defensive screen that took days to fill. The Houthis noticed. They attacked during the gaps. In May, the tanker Wind took a ballistic missile hit that killed her propulsion. In June, the bulk carrier Tuta was hit and sank. Days later, the cargo ship Verbena was struck. 3 ships were hit in the windows between one destroyer leaving and the next one arriving. Go back even further. February 23, 1945, the ammunition ship USS Shasta pulled alongside the carrier USS Bennington in the open Pacific and transferred bombs using a cable rig known as the Burton transfer method. Winches, booms, cargo nets. Crude, dangerous, effective. Sailors manually handled ordnance between 2 ships steaming side by side at 12 knots. It worked because a 500-pound bomb is a steel sphere. You can roll it, cradle it, absorb impacts. It tolerates rough handling. Now compare that with what sits inside a VLS cell. A Tomahawk canister is not a steel sphere. It is a 20-foot precision instrument, packed with volatile propellant and a concentrated warhead. There is no cargo net that solves that problem. There is no Burton rig that threads a 500-pound needle through a 25-inch opening on a moving deck. For 80 years, the Navy has transferred fuel, food, and ammunition at sea. But the one thing it still could not transfer at sea, the one piece of cargo too delicate, too dangerous, and too precisely dimensioned, was the missile that defines its combat power. The Navy knew this problem was coming. In 2022, the Johns Hopkins University Applied Physics Laboratory began designing a system called TRAM, the Transferable Reload at Sea method. The concept was radical in its simplicity. Eliminate the pendulum. Instead of hanging the canister from a cable and letting it swing freely while the ship moves underneath it, TRAM grips the canister in rigid hydraulic jaws. No cable, no free-hanging load, no pendulum. The canister is locked into a rail system bolted directly to the VLS module structure. The ship moves, the rail moves, the canister moves. Everything becomes one rigid body. And once that happens, the physics of relative motion between the canister and the cell disappear, because both are physically tied to the same frame. Here is how the process works. A replenishment ship, a Lewis and Clark class dry cargo vessel like USNS Washington Chambers, comes alongside the destroyer during a standard underway replenishment. The missile canister crosses over using the existing UN rep cable system. Once aboard the destroyer, TRAM's hydraulic arm seize it. The rail moves it horizontally into position over the selected cell. The mechanism then rotates the canister from horizontal to vertical, a full 90 degrees. After that, an integrated cable and pulley system riding inside the rigid rail lowers the canister into the cell. The entire sequence is controlled by hydraulic power, not by gravity, momentum, and hope. No pendulum, no swing, no luck. On July 15, 2024, TRAM completed its first land-based test at the Naval Surface Warfare Center in Port Hueneme, California. On October 11, 2024, it went to sea. Sailors aboard the cruiser USS Chosin CG-65 used TRAM to load an instrumented test canister into a Mark 41 VLS cell while underway off the coast of San Diego in Sea State 4. Not the worst the Arabian Sea can deliver, but real enough to validate the engineering. The canister slid in. Secretary of the Navy, Carlos Del Toro, called it a game changer. Then, in July 2025, a second at-sea test aboard the destroyer USS Farragut, DDG-99, during large-scale exercise 2025, demonstrated faster reload rates, proof that the system could scale. The Navy planned to field TRAM across the fleet by late 2026 or early 2027. Operation Epic Fury began on February 28, 2026. TRAM was not there. The machine that solves the pendulum, the machine that ends the 3-week bleeding loop, was sitting in a development pipeline, while the fleet burned through 850 missiles without the ability to reload even one of them at sea. Now step back, because the full picture reveals something larger, something TRAM alone cannot solve. TRAM eliminates the pendulum. It replaces the 3-week round trip to a concrete pier with a 4-hour replenishment alongside a supply ship 30 nautical miles behind the battle line. When it is fielded, and it will transform naval logistics. Destroyers will stay on station, presence gaps will shrink, the bleeding loop will close. But TRAM does not create missiles, it only moves them, so run the numbers again, slowly. The United States Navy fired more than 850 Tomahawk cruise missiles in 5 weeks. That is the highest expenditure of a single precision weapon system in any conflict since guided missiles were invented, more than the entire 2003 Iraq campaign. RTX, formerly Raytheon, currently produces Tomahawks at a rate of about 60 to 90 missiles per year, a sustainment pace designed for peacetime budgets and peacetime assumptions. 850 missiles in 5 weeks, 60 to 90 produced per year. The fleet burned through roughly 10 years of production in 35 days. Yes, the defense industrial base is reacting. RTX signed framework agreements in February 2026 to scale production toward 1,000 missiles per year. But each Tomahawk still depends on more than 100 subcontractors, thousands of precision parts, and a production lead time of 18 to 24 months from order to delivery. Scaling a factory is not a software update. It is machine tooling, supply chains, and skilled human hands. Now go all the way back to Vector 1, the pendulum, the crane, the trade that gave us 96 cells instead of 90. At the beginning of this video, removing the strike-down crane looked like the mistake that created the problem. But here at the end, the picture changes. Even if the Navy had kept those cranes, even if the pendulum problem had never existed, the magazines would still be empty because the factories cannot refill them fast enough. The real constraint is not distance, it is not physics alone, it is time. The time required to forge metal, assemble guidance packages, test propulsion systems, and deliver a finished missile to a fleet that can fire them faster than any production line on Earth can build them. TRAM solves the first equation, how to get a missile from a supply ship into a VLS cell at sea. It does not solve the second equation, how to make sure there are enough missiles on the supply ship in the first place. Epic Fury is the first conflict since World War II in which the United States Navy has consumed precision munitions faster than its industrial base can replace them. That is not a weakness, that is a new category of problem. Any force powerful enough to fight a sustained, high-intensity war will eventually collide with it. Because the physics of manufacturing do not accelerate, just because the physics of combat demand it. If you now see factories instead of warships when you think about naval power, subscribe to Navy Decoded and share this with someone who still believes wars are won by the weapons that fly instead of the machines that build them. Now go back to the image we started with. A $2.50 billion destroyer turning away from the fight at 2 in the morning, 96 cells, all empty, heading south toward a concrete pier and a crane bolted to the ground. 3 weeks out of the war, the Navy built that ship to carry 96 missiles. It removed the cranes that could reload them and got 6 extra cells in return. For 25 years that arithmetic worked. 96 was enough. Then came a 5-week war that burned through 850. TRAM fixed part of that equation. A hydraulic rail bolted to a VLS module, a 500-pound canister clamped in rigid jaws, lowered into a launch cell at sea while the ocean tries to throw it off. The pendulum, the same physics that defeated every earlier attempt, is finally removed. Destroyers will reload alongside supply ships instead of retreating to port. Presence gaps will close. The bleeding loop will end. But TRAM moves missiles. It does not build them. It takes 18 months to manufacture a single Tomahawk cruise missile. It takes 12 seconds to fire one. So the machine that matters most in modern naval warfare is not the radar that finds the target. It is not the missile that strikes it. It is not the VLS cell that launches it. It is not even the hydraulic rail that reloads it. It is the machine on the factory floor, the one that turns raw metal into a guided weapon. And that machine does not answer to admirals. It answers to physics. The physics of metal, heat, and time.